alaikum. We'll be continuing our lecture on organic chemistry. Up until last class, we were observing that we introduced with the term heteropolymer and homopolymer. Actually, I sort of gave some misinformation. Like it was actually not in misinformation. I was like lacking some information on the concepts, but Alhamdulillah, like I'm currently having some grasp of the knowledge. So basically, what is homopolymer and heteropolymer? The first, like I at first mentioned about homopolymer and heteropolymer. Then after that, I defined something else. I defined that homopolymer is like a single chain, while heteropolymer is like there might be many chains, but homopolymer actually means the monomer made of like a single monomer. Okay, like there is just simple type of monomer. For example, either this or this or this type of monomer. Heteropolymer is combination of like two or more monomers. That means the polymer which has been formed might contain different monomers. That's what heteropolymer means, and homopolymer means like same type of monomer. That's why like you could say hetero means like something which is hated. Like this is some sort of thing which I use in order to like recall, okay, what does homo and what does hetero mean? So homo means similar or same, and hetero means like, for example, two person hate each other. That means like, or like they differentiate in their like characteristics. So that means two different monomers. Okay. Now let's come to today's part where we're going to start with our concept on, like we are going to study more about the component Kevlar. We, in our last class, did sort of studied a bit about Kevlar. So Kevlar was what? Kevlar was polymer, which is actually more specifically known as like a tough polyamide. So there is this amide linkage. There is going to be an amide linkage, which is CONH, and that amide linkage is sort of causes that amide linkage sort of makes this Kevlar. While Kevlars are usually used in bulletproof vests because due to their like very like their rugged, rough characteristic. Okay. Now we also defined that there are some sort of polymers which we'll be actually discussing in our today's class. One is HDPE, another is LDPE. HDPE is what? So HDPE is high density polyethylene, while LDPE is low density polyethylene. Okay. Before coming to this, let's have a little bit of information which I left behind about Kevlar. So in Kevlar, the polymer strand, okay, the polymer strand, it can line up to form strong sheets with bonds between the strands. Now, what does this strand means? Let's say we have a polyamide or a Kevlar. Okay, so let's say this is our Kevlar molecule or polymer. Okay, so let's say we have this polymer. This polymer is known as one strand. Another strand would be, let's say, here is another strand. Let's say this is another strand. Okay, this is another strand. Now, what does this like two strand can have? Remember, in our AS context, we have studied there can be bond between like there can be hydrogen bond between nitrogen hydrogen, oxygen hydrogen, okay, fluorine hydrogen. These are known as hydrogen bond. So n between N and H there can be a hydrogen bond. Between oxygen and hydrogen there can be a hydrogen bond. Also between fluorine and hydrogen there can also be hydrogen bond. This is in the topic of most probably like the bond chapter. Okay, so there the topic is mentioned there as hydrogen bond. There specifically these hydrogen bonds are given, who can form hydrogen bond, who cannot form hydrogen bonds. Okay, now here we can see actually there is the presence of nitrogen and hydrogen. It doesn't have to be like ionic compound. This also happens with covalent compounds. We just need nitrogen and hydrogen in this case. Now in this case, we do have nitrogen and hydrogen. So they are saying that Kevlar, the polymer, like one of the polymer strand can have, or this lineup can form strong bond with another sheet of, or another strand of the Kevlar, okay? That means here is this hydrogen of like hydrogen bonded with the nitrogen, and here is the oxygen bonded with the carbon. They together can form hydrogen bond. Similarly, this hydrogen of nitrogen and this oxygen of this carbon, they also can form sort of this hydrogen bond. Here also can hydrogen bond can form, and similarly this can goes on. Now, just a minute. So here we can have some partial charge actually, like oxygen is what? Partially negative charge. So delta minus, and hydrogen is partially positive charge. Due to this state, they sort of attract each other from this bond. So this bond actually can be shown in this way. Oxygen, after forming its bond with the carbon, here we have two bonds, here we have two bonds. Oxygen have further two lone pair of electrons, isn't it? Now this sort of acts like attracts this hydrogen. Similarly, over here we have two more like lone pair of electrons from oxygen. So oxygen is partially negative charge, but hydrogen is partially positive charge since it does not have any lone pair of electrons. So they tend to attract each other. Similarly, this oxygen as well, partially negative, partially positive, they sort of attract each other, forming that strong bond between the strand. Okay, so this is the information to be given. Now let's come to our today's topic, which is HDPE and LDPE. HDPE stands for high density polyethylene. Okay, now about this high density polyethylene, like the polymer chains of this high density, if for example the polymer chains have strong van der Waals forces of attraction. I'm just mentioning the characteristics. So here we have to have polymers have strong van der Waals. I hope you recall what is van der Waals forces of attraction. That is like attraction between two covalent molecules. So it is actually the bond due to the electron. Okay, so for example, this is a molecule, this is a molecule. They have attraction between each other due to their electrons. This is known as the electrostatic attraction, or you can say, okay, like sort of electrostatic attraction. So polymers have strong van der Waals forces of attraction. Then polymer chains, they are closely packed. So the chains or polymer chains closely packed. They must be closely packed. That means nothing like think about gas. What are they? Gas are spread apart each other, isn't it? But this sort of polymer, there should be closely compact. If free space is there, they're going to fulfill that free space as well. Okay, so that's how or what these chains usually have the structure of. So they're closely packed. Now if such a situation is there, that means what? There will, like, to break these bonds or to break this structure, we would need what? More energy. So more energy to break the bonds or to break van der Waals forces of attraction, isn't it? So this is the characteristic, or this is the characteristics of HDPE. So how do usually HDPE looks? HDPE looks like something this. Let's say this is a strand, this is another strand, this is another strand. Okay, let's say this is a Kevlar molecule, and I'm drawing each of the strands. These strands are closely like packed with each other, like they're consecutively like beside each other. Okay, so this is actually, let's say, HDPE. Okay, that means it has what? This, since like it has higher van der Waals force of attraction, that means it has high melting point. Okay, this has a higher melting point. Now, in order to make things easier for you, let's describe the LDPE, which is low density polyethylene. Low density polyethylene. Now, what does it have as a characteristic? Same things like in the opposite way. Okay, so as like HDPE, these are the different like opposite way. I would urge you to pause the video and just guess what should be the characteristics of like low density polymerization or polymers. Okay, so they have weak van der Waals. Then they have like, okay, I will explain them later, but let's just first like finish the characteristics. So weak van der Waals forces of attraction. Then they have like they're loosely packed, loosely or less closely packed, less closely packed. I mean the strands or the chains. Then the like as this is the case, they require less heat energy to break the bonds, to break the van der Waals forces of attraction. That means what? They have lower MP or melting point. Okay. Now let's see a structure of the like LDPE. You might think, yes, obviously they're further apart, loosely packed. Yes, there is, but there is something else. Why are they loosely packed? Because if like think, if you have enough space, obviously you would try to fill that space. But this is not the case because they have branches. They have branches which sort of like interferes them from like filling the spaces. Okay, they have like branches. What are these branches? Let's say we have this we have such molecule. Okay, and if one of the part, let's say, contain this part, okay, that means what? It has a chain. It has a branch, so chain, or like this is the branch of the chain. Okay, that means this sort of branches actually, these branches, like this is an example, not exactly like these branches are going to be this component, this can be many things, but I'm just, for example, I'm giving this. So let's say like tree branches, so they, like as like tree branches, there are like, so like this branch, like this portion or this like this structure, this is causing them or preventing them from coming close to each other. That means what? Now van der Waals forces of attraction are between whom? There are more now between them, isn't it? Now between them, between them, between them. Like they're sort of like in between this, like between the branches, isn't it? Because now the other parts are like they're further apart. So this like these are the like between branches they have van der Waals force of attraction, and like they can have actually between the like between the chain and the branches as well. But think from one branch to another branch, sorry, one chain to another chain, the distance actually happened what? It increased, isn't it? But previously, let's go back to the HDPE. What happened? They can have like they have what? Higher contact area. They have greater contact area. Like think it in this way: you have your two hands. This is your one hand, like one hand's, let's say the bottom surface, and this is another hand's bottom surface. If you place them together, okay, you have two hands, you have a greater surface area, isn't it? Like you have greater contact area. Now think, like this is your, like this is one of your hand, okay? Let's say this is one of your hand. I'm just sorry for my drawing, but one of your hand and another of your hand, like you're keeping it in the same way, just holding them together, okay? It's like this is your hand in that structure. Now let's consider you're just touching with fingers with each other. Now think which one have like greater contact area, greater connection. This one has greater connection, isn't it? It is like composed of a wide area, while this is just a single point. That means when you have wide area, you have solid grip, you have greatest like greater van der Waals forces of attraction. Why? Because more electrons are now involved with each other. But here you have just electrons from these 2 points, but here you have electrons from all over the surface. That means in HDPE there is greater van der Waals forces due to like high contact area. So that means HDPE has, you can say, more surface or contact area. Okay. However, in LDPE we have less contact or surface area. Okay. Now let's move on to our next part. I hope you have got it, what HDPE and LDPE means. Moving on to our next part, which is hydrogel. Now, what is hydrogel? Now, hydrogels are basically, or you can say they are like hydrophilic structures who can absorb large quantities of water. Now we have come over two concepts. One is hydrogel, and while defining hydrogel, we encounter the term hydrophilic. Hydrogel and hydrophilic. We have so far studied about electrophilic and nucleophilic, but what is hydrophilic? Well, let's at first define the characteristics, then we will define. So these are what? These are hydrophilic, hydrophilic. They are hydrophilic and they can absorb large quantities of water. Okay. And the second point is the hydrogel is formed from chains of one polymer which are cross-linked using another molecule. Formed from chains of one polymer which are cross-linked using another molecule. I'm just writing things in short, okay? I'm not in detail writing. So it's like I would urge you to write the things in whole words so that while revising, you understand your own language. I'm just writing like, since like due to time shortages, I'm writing them as points, okay? Using another molecule. Now, how and what does this mean? Hydrophilic, at first, let me say what does hydrophilic means. Now, hydrophilic means a thing or a substance where you have, let's say, how do I define this? Let's say, okay, so hydrophilic means it can sort of, like it has a tendency to react with H2O, okay? If they're, like, if the, let's say the molecule, like this is the structure of water. Now the molecule, let's say it sort of breaks this hydrogen and one of the portion reacts or forms bond with this hydrogen and the part of the polymer forms bond with this part, okay? Now that means what? Like water molecule, like the water molecule disappeared. So the water molecule is being used up or absorbed by the hydrogels, okay? Let's see a structure. This might be easy for you to understand then. Let's say we have a structure like this. let's say we have this molecule. Okay, now this is not just a single molecule, there's 3 different molecules. One is this one, the above one, another is, let's say, the bottom one, I mean the middle one, another is the bottom one, which like this part continues, this part also continues, yeah, this part also continues. Okay, so now what do we have? According to the definition, this means the hydrogel is formed from chain of one polymer which are cross-linked using another polymer. Okay, let's see. This is a chain. Okay, the abovemost portion is a chain. Let's say, let's define this way. This is a chain. Why? This is a hands-free. That means it continues. That's a chain. Another chain is over here. This is another chain. It is also having a like open hand. That means what? It continues in this way as well as in this way. This is actually CH given. Okay, so this continues on the right towards the left. That means this is a chain. These are 2 polymers. See, this is like this middle portion. This is not forming any bond like so far. Still, it is like no bond is formed. How do I know? This is a carboxylic acid. This is alcohol. They should have reacted to form ester, but they are going to form that, but so far didn't happen. This is also an alcohol. The bottom one is a carboxylic acid. Okay, so what is happening? See this part. This is not a polymer. Okay, this molecule itself, it is not a polymer. It's like sort of some substance, like some molecule. So some molecule. This is going to link this together. How? The above alcohol is going to react with this carboxylic acid, and the bottom alcohol, the bottom alcohol is going to react with this carboxylic acid. After reaction happening, what will happen? This will be bonded. There will be an ester linkage that is going to cross-link home. This main chain and this main chain both will be cross-linked due to this forming bond of like this alcohol, like this ester linkage. That means what? There is this cross-link between 2 polymer chain. Now, what is going to happen is, let's say, yeah, so we do have yes, since we do have such a whenever, let's say, just a minute, let me define how I can this is actually OH. Yeah, so this was OH. So there are like 4 alcohol in together. So this is actually known as our penta okay, whatever it is. So some name penta I'm not sure, like it's written here, so I'm writing it again. So this is the name of this molecule. You don't need to know, just I'm defining it like just for extra information. But this is the structure so far. Now, when this bond is formed, these molecules, they can form hydrogen bonds with water. Now, who can form hydrogen bonds with water then? Now, what I try to make thing like make sense is, for example, here we have alcohol, here we have alcohol. They can form the partial bonds with water molecules. Then we have, let's say, the other carboxylic acid groups, or we have this like this bonded groups of ester. Wherever we have, let's say, oxygen, we have like free oxygens there. They have the tendency to form bond with hydrogen more, because now we have greater number of hydrogen, the greater number of oxygen in the molecule. We have now greater number of oxygen. That means they can absorb more of waters. Now, one thing to mention is, let's say we have this molecule. This is an extra information. So this molecule, it can form, let's say we have this carboxylic acid here. And let's say we have another molecule. which is just a salt of the carboxylic acid. This is the structure, okay? And we have also over here, this is the same part with carboxylic acid again. So we're trying to make a, let's say, a polymer, okay? Now these three, they react, both like they react, I'm writing it in the bottom part, they react to form, let's say, this longer chain. And it's free, carboxylic acid, CH, like this is going to have an addition polymerization. We'll have addition polymer here. And it continues, let's say. Okay, it continues. Now, due to the presence of this COO minus, okay, we have the presence of which groups? COO minus and Na plus. Okay. Now, due to this presence, what happened? They can form stronger bonds with water. Now, in carboxylic acid, what happens? In carboxylic acid, we have COOH. They can partially ionize to form what? COO minus and NH plus in water, isn't it? That means what? That means they actually partially ionize. That means they have partial charge in that case. But here they're completely ionized. This is an ion, this is an ion. Okay. This is an ion, this is a cation. So they can directly form bond with, let's say, hydrogen and like water molecules. Okay. They can form direct bond with like water molecules. But here they have to form partial bond with water molecules or less number of bonds with water molecules compared to this one. That means what? If our structure somewhere have, let's say, instead of carboxylic acid, in the above structure we have, let's say, there is our carboxylic acids. Okay. Instead of carboxylic acid, if we have sodium bonded with them, so COONA, that means what? They can form stronger bonds with water. That means well, greater hydrophilic characteristics. Hydrophilic characteristic is that which can absorb more water. So hydrophilic characteristic increases. Okay, now this substance, the sodium, like this part, this sodium propanoid. So this is actually what? This was 1, 2, 3. So propanoic acid, isn't it? This is propenoic acid. And this is sodium propenoid. Okay, this is a sodium propenoid. Now this sodium propenoid, it has an industrial use. How this industrial use is like maintained, or in which industry is it used? It is used in, for example, the like in making of, let's say, the baby diapers. So you have seen the baby diapers, they have like the a gel inside them. So that gel is actually the hydrogel. That hydrogel helps to absorb the absorb the water, and hence the babies, they sort of stay dry for a longer period of time. That means hydrogels are used to absorb greater amount of water, and if more hydrophilic characteristics the hydrogel have, that means what? They have the greater ability to absorb more water. Okay, so there you go. I sort of gave an advertisement about a product, but yeah, no branding I used, so being neutral in that case. Now let's move on. Now we have the structure of protein. So protein is also known as polypeptide. You'd see a similar sort of linkage as amide, but amide has a specific way of like writing them. In peptide, it can sort of, just a minute, let me see. No, sorry. In peptide, we have specific structure. Peptide, we only will have a specific structure. So in peptide, you will see we will have just CONH. Peptide will be CONH. We cannot have NHCO. So this is a synchronized way, maintaining a same structure is known as peptide. Okay? So what are peptides? What are proteins are formed due to condensation polymerization. Okay? So formed from condensation polymerization. Okay, I'm writing in short, condensation polymers. Now, the monomers are what? Monomers are the famous amino acids. Monomers are amino acids. So that means they are going to have this structure: NH, H, we have C, H, C, OH, but there is one thing left, which is this R group. That means this R can actually change. Now, what can this R be? This R can be, let's say, glycine. Glycine is what? We represent this glycine as GLY. These are actually given in your data booklet. You can see it most probably in the last page or before, like few of the in the last page in the organic chemistry part. So then we have CH3, which is known as alanine or alanine, which is represented as ALA. Then the R could be CH2COOH. So this is actually like the forming bond. So this is known as aspartic acid, which is ASP. Then we have CH2SH. This is actually terms used more in the biology, so you'll be understanding these concepts more from the biology subject. But here we have some implementation of the topics or the substance. So this is known as cysteine, whatever it is. Unfamiliar with the pronunciation of this sort of molecule. And then we have CH2OH, which is actually serine or serine. And finally we have, there could be more, but these are the fundamentals of the most general one. And this is known as lysine. This is represented as LYS. Okay. Now, if let's say this R, R of one chain, let's say one of the molecule is amino acid is given, and we have this R chain there, one of the R chain is present there. Okay, any one of them could be here, from this given one, let's say any one of them is there, and let's say take for example, we have this CH2 COH, that means aspartame, most probably, isn't it? This is aspartic acid, sorry. So this is aspartic acid, ASP. So this aspartic acid, and the other molecule has this CH2, that means the last one. Just I represent this as CH2 for shorter version, NH2, which is lysine, LYS. Then what happens is they sort of form hydrogen bond. They form hydrogen bond. How do they form hydrogen bond? Now, hydrogen bonds main target is having hydrogens. Okay, hydrogen bond. So far, I have described that this is carbon, oxygen, and there is this hydrogen. They sort of forms bond, but our main target is having hydrogen bond between them, or forming hydrogen bond between, just a minute, molecules where especially hydrogen is involved in either of the molecules. For example, either nitrogen will have a hydrogen, either oxygen will have a hydrogen, or either fluorine will have a hydrogen. Okay, so they are going to, these hydrogens, not carbon having hydrogen, they are not going to participate in hydrogen bond. Only the hydrogen bonded with nitrogen, oxygen, or fluorine, they are going to participate in hydrogen bond. So that means this is the molecule, and we have carboxylic acid and NH2. They are going to form additional hydrogen in between them. One of the bond is what? They will form peptide linkage. Two monomers will form peptide linkage. But another is, if they have in between them this sort of R groups, which is aspartic acid, and let's say, let me show you. Let's say this is our amino acid. This is the R part. Let's say instead of R, we have H2COOH, and we have, let's say, the another molecule where we have, let's say, the lysine part, which is CH2 4, and we have, let's say here, NH2. this NH, like this hydrogen from nitrogen and this oxygen from this carboxylic acid, they are going to have the hydrogen bond, and the rest of the amino acid will like continue. Let's say this, like there's this chain, and the other chain will be like, let's say there's this another molecule, so this will like sort of polymer will go on. Okay, now protein is known as like a condensation polymer, isn't it? After condensation polymerization of the amino acid, protein is formed, joining the bond and forming what? The peptide linkage. Okay, now formation of dipeptide could be, let's say, a formation of di dipeptide. Let's say we have alanine and glycine. Then molecules would be NH, CH, CH3, C double bond OH plus H, NH, CH, COO, OH. When they form bond, they have, let's say, this structure. This is not like so far we didn't form a polymerization. This is just like condensation happening. Okay, and when condensation happened, what do we know? Either water or HCl will form based on what eliminated. In this case, this part and this part eliminated, forming our side product as what? Water. You don't need to write the water in this case, but we have to know that this is the molecule being formed. So this is our peptide linkage. Okay. In our next part, we will see that the formation of tripeptide, how that could be formed. Then we have today's last topic, which is zwitterion. Okay.